we present occlusion-free scene recovery via neural radiance fields. In real world, opaque occlusions can block useful information from reaching the camera. The occlusions range from scribbles, fences, water drops to any undesired objects at the foreground, in front of the desired background, and removing them is the main goal of occlusion removal. The occlusions can challenge many downstream vision tasks, such as scene understanding, segmentation, object recognition, etc. Structure from motion may also fail in scenes with occlusions, since the features in the images may not match due to their being blocked in some of the views. That makes obtaining an occlusion-free scene representation prominent and challenging, which is the goal of our paper. With multiple viewpoints, we can aggregate an occlusion-free neural radiance field, due to the fact that an object may be visible in some of the input views. The intuitive idea behind our work is that we only supervise the background representation on the area where background is visible. To directly obtain an occlusion-free neural radiance field, related methods only try to remove transient objects. NeRF in the wild tries to separate the scene into a static part and a transient part. Hallucinated NeRF learns a visibility map indicating the probability of being static, and only supervises the NeRF representation in static area. The problem is that both works rely on pre-computed camera poses, and they cannot remove static occlusions by design. Another way to tackle with the problem is to apply occlusion removal method as a pre-processing, before a vanilla NeRF representation is constructed. Note that we only consider occlusion removal using multiple images, since inpainting is an ill-posed problem, and either relies on user annotation, or can only work with certain types of occlusions. We choose loose work at CVPR23 as a state-of-the-art multi-image-based occlusion removal method. It estimates the optical flow from the input images, and separates the background and foreground layers. However, this thread of work does not explicitly model the 3D space, and thus is not 3D consistent, which may lead to the failure of NeRF reconstruction. In addition, the input views should be very close to accurately estimate optical flow. To deal with the problem that structure from motion may fail, while removing the occlusions, we propose a joint optimization of pose refinement and scene reconstruction by effective multi-view feature fusion, and a self-supervised occlusion detection and removal scheme via neural radiance field. We divide the whole pipeline in two parts, and introduce the joint optimization first. We set the camera parameters as trainable components, and jointly optimize them with a scene MLP, colored in blue, which will reconstruct the scene with occlusions. This step provides our method with a coarse estimation towards the geometry of the scene. During sampling, we fetch the corresponding feature scene from multiple neighboring views. These features are only used to construct the cost volume. So here is the intuition about cost volume: the less similar a point looks in different views, the less likely it is a visible point. Mathematically, we refer to the variance of the extracted features. Here we show two results of the joint optimization, and comparison with vanilla NeRF and NeRF-, which also jointly optimizes camera parameters and NeRF. The proposed method notably gets the scribbles in the foreground right and generates less artifact, because it uses the multi-view clue in a more explicit manner. With the aforementioned joint optimization, we can obtain an accurate scene reconstruction result. Next, to remove the occlusions, we propose a selective supervision scheme, where the rendering results of background MLP is not supervised in masked region. But first, let's look at an intuitive definition of occlusions. In this illustration, to look at the object from the camera, and from infinite far, yield to expected ray termination depth. Note that ray termination means that the points behind the depth do not contribute to the rendered color of the ray. The inconsistency between the two ray termination depth, or bidirectional depth inconsistency, reflects the presence of occlusion. When bidirectional depth inconsistency is small, there is no occlusion. And when bidirectional depth inconsistency is large, there is occlusion. We then use a mask MLP to learn the probability of the ray not hitting any occlusion, and supervise its training by bidirectional depth inconsistency. Binarization is applied to the output probability, and only the region without occlusion is used for supervision. Take the two scenes here as an example. The area corresponding to fences and scribbles are not used for supervising background MLP. And the occlusions are indeed removed in background MLP, since it has not seen any occlusion during training. And this is the whole pipeline. Through the two steps, we can obtain an occlusion-free scene representation. Here we show one sample from each scene in the dataset. The dataset not only contains multiple sparse viewpoints of occlusion scenes collected by ourselves, but also selects 4 scenes from existing datasets, to increase the diversity of capturing conditions and occlusion types. The rest 6 of the scenes are captured by ourselves using a DSLR camera or an iPhone 12. We show some results. First, for the statue scene, HaNerf generates the worst reconstruction results. Presumably visibility map removes nearly all of the useful information in the images. Lu's work also failed to separate the foreground from background clearly, and yields a NERF with a lot of artifacts. NERF in the wild does not recognize any transient occlusions in the input images, and keeps the occlusions as they are. For our method, based on the accurate estimation of the scene MLP, the background MLP effectively produces results, free of occlusions. Here is the scene of Scribble 3, and we can see similar results. In the case of Raindrop, all the baseline methods fail due to the failure of the structure from motion method, ColMap. The scene MLP still synthesizes realistic results with raindrops, and the background MLP recovers the background clearly. For more results, the audience are encouraged to visit the project page, or refer to our paper for more details.